Hello, everyone. Welcome to another episode of Science and Technology Q&A for kids and others. And I see that there are a bunch of questions here waiting. Let's start off with the one I see at the top here from Eddie. Considering visual perception discontinuous or discrete, can we consider it quantized? In that case, could it be calculated as discrete packets of visual perception based on quantum physics? Oh boy. Okay, so first thing to say is that when we think about light, our eyes are sensing light. And the way that our eyes sense light is that the retina, the back of our eye, has photosensitive cells. And in those cells, there are protein molecules that have the feature that if a packet of light hits that protein molecule, it causes it to essentially produce a piece of electric current, produce an electron that is then then causes electrical activity in our nerve, in our optic nerve, that then goes to our brain, that then causes us to have the sensation of seeing something. Okay, so at some level, our visual perception is necessarily discrete because it comes about by a packet of light hitting a specific molecule on our retina and producing a specific electrical effect. And now, I said a packet of light because I'm kind of hedging there. The question is, what is light kind of made of? And is light a sort of continuous sort of wave of electromagnetic radiation, or is it broken into discrete sort of corpuscles, discrete particles? Well, what quantum mechanics tells us is that we can think about it in either way. We can think about it either as this kind of stream of particles, photons, whose characteristics we can only figure out on average, but we can think of the light as being broken down into individual photons. It's just that when we sense those photons, we only sense them in some average way. So that's choice number one. Choice number two is the idea that light is part of this continuous field, this wave of electrical effects and magnetic effects that are producing that represent light. And that those two points of view, one of the discoveries of quantum mechanics in well, this was really in the 1920s, was that those 2 points of view kind of give you mathematically the same results. When you ask, what is the perception of a piece of light? It doesn't really matter whether you think about the light as being this wave or whether you think about it as being these discrete photons. You get, when you're looking at the mathematical effect of how an observer of the light senses the light, you get the same consequences in those two cases. But in terms of the way we think about something like the rhodopsin is the name of the protein that is is responsible for, yes, I have that right, I think, is responsible for sensing light on our retina, but that really operates, it's best to think about that in terms of a single photon of light hits the protein molecule, it causes it to eject a single electron that then goes and produces electrical activity on our optic nerve. Okay, so one of the questions that one might then ask is, if it is the case that there are these discrete sort of pieces of light, these discrete photons that we sense, that are responsible for what we sense in our eyes, how come it looks like there's sort of continuous levels of light in our eyes? How come we're not seeing the little points of light all the time? How come, particularly when there's very little light and when it's very dark, how come when it's dark, do we not start seeing, does our visual scene not start being little points of light coming in, rather than just, oh, I can barely see it? Why is it the case? Why isn't it the case that it's like, oh, I see a little, that was a photon that came in there, that was a photon that came in there, and so on. Okay, it's actually slightly mysterious why we don't see that. And it is more a feature of our visual perception than it's a feature of the physics of light. And the reason we don't see it, presumably, is because our we have sort of nerves that cross-connect between these different photoreceptors on our retina, and those do a certain amount of averaging. And so it is, even though at the lowest level, there would be individual cells in our retina that are sort of being excited by these photons of light, we're the kind of net of nerves that even exists in our retina averages the effects of those different individual photoreceptors. And so the things that we sense never corresponds to things where we can actually see individual photons. Now, the architecture of our eyes, the eye, the compound eye of the type we have, has evolved 3-4 times separately in the course of biological history. And things like, I think, the king crab has a different lineage of its compound eye. It's the same idea. It has photoreceptors, same as we do, but its eye seems to have evolved in a different path. It sort of differently emerged from lower level visual perception apparatus. And it doesn't have a mistake that we have in our eye. In our eye, the photoreceptors are on the back, and there is in front of the photoreceptors are some of the connections between the photoreceptors, and that absorbs some of the light that we would otherwise be able to see. The king crab, I guess, really put a premium on being able to see well because it lives in deep enough in the ocean. There really isn't very much light there, and so it managed to get this right and has the cross connections behind the retina, which means that it is more sensitive to light than we are. And I think the claim is that there are at least the king crab should be able to sense kind of, well, at the very least, like a 50 photon lump of light, but distributed across its whole retina. So that probably means that if we were king crabs, we probably already know about photons, because one might suspect that the perception system of the crab actually is sensitive, would perceive low light levels in terms of individual photons coming in the way that we do not. So now that's the case so in other words, you can't sort of discover the quantization of light. You can't discover the fact that you can think of light in terms of photons by our visual perception, because we're doing all this averaging, which is specifically making us not notice that there are sort of individual packets of light coming in. Now, there are cases in which you can see the equivalent of when you so when you have when it's not just your eyes, for example, when you have a photomultiplier tube. So how do you detect a photon? You well, let's see, that actually we want a different well, for example, let's take, maybe we shouldn't get into this particular rabbit hole. I was going to talk about night vision systems and things where you have an effect of a photon comes in, and it's a little bit like what happens in our retina. The photon is converted to an electrical signal, and then what happens is you're amplifying that electrical signal, and there are a variety of ways that can happen. You're using electric fields, magnetic fields to sort of amplify in different cases, it's done in different ways to amplify that electrical signal. It's very hard. If you have a photon, if you have some light, there's no easy way to just increase, you've got some light coming along. There's no easy way to sort of increase the light signal directly. For an electrical signal, there are ways to amplify the electrical signal, to kind of feed in more energy in effect into the electrical signal to make it a higher signal. There are a variety of ways to do that and so that's why one tends to do amplification in electrical terms, not in terms of light. You can do amplification of light with lasers effectively. That's again a separate story. All right, a little bit on that. Let's see. Parmenides asks, if the level of carbon dioxide in the Earth's atmosphere was much higher in the past, why wasn't there a runaway greenhouse effect back then? I don't know for sure. One thing you can certainly see, we have data from a variety of sources that give us an indication of the carbon dioxide and oxygen levels in the Earth's atmosphere and the average temperature going back throughout geological time. And so I don't recall the exact times. I think in the times of the dinosaurs, the carbon dioxide level may have been higher, substantially higher. Certainly the Earth has changed a whole bunch over time. The temperature of the surface has changed. There are ice ages, even in recorded history, even in the 1600s, there was kind of a little ice age, and you know, rivers that nowadays are sort of free-flowing rivers in Northern Europe, for example, were frozen over for 50 years and things. It never got warm enough to melt that ice. So that was, I think, 1650s, if I remember correctly. Around that time, there was kind of a little ice age that had an effect. And there are all kinds of strange correlations between, for example, solar activity, sunspot activity, things like that. There's effects like that. There are effects to do with the precise distance that the Earth is in its orbit away from the sun, and there's cycles and the tens of thousands of years range on that. So there are a variety of these kinds of very externalized effects that can have an effect on the Earth's average temperature and things like this. Then there are features that are more to do with the biosphere part of the Earth. I mean, you know, plants, you know, absorb carbon dioxide, animals produce carbon dioxide, things like this. I think that the question of what, I should explain something, which is that the reason, okay, so there's this phenomenon, the so-called greenhouse effect. I should explain that. So in a greenhouse, that is, you know, a glass sort of, you know, shed or whatever it is that in which you grow plants and things, you've got, you know, it has a transparent roof, but that roof it's transparent to visible light. You can see through it, and the sun, light from the sun, which most of the light from the sun is visible light. The light from the sun perfectly well goes through the glass. Just like we can see through the glass, light can get through the glass, ordinary light can get through the glass. The problem is that once that light, so light comes in from the glass, when that light, the energy from that light heats things up, those things, they get hot, and they are, when they get hot, they also emit something like light, but it's infrared light. So let me try to explain this. So whenever you have a hot object, it is, you know, heat is all what heat means is it's the energy of all the molecules bouncing around inside the material. That is what corresponds to heat, and the sort of the energy, the average energy associated with all the molecules bouncing around, that determines the temperature. So what happens is that as all these atoms keep on colliding with each other and things like that, the effect of those collisions is to make the atoms emit light. And they do that because the atoms get, well, because the electrons inside the atoms get they get sort of kicked into an excited state, and then they emit light when they decay down to the ground state again. But in any case, the basic effect is when there's all this, you're producing these, you're producing photons of light. But now the question is, as you change the temperature, how does the spectrum of light that you produce change? And what happens is, this was discovered around 1900. What happens is there's the so-called Planck spectrum, named after Max Planck, P-L-A-N-C-K, Planck spectrum. And what happens is that so you get light or more accurately, electromagnetic radiation photons, whatever you want to describe it as. You get essentially photons of a range of different energies produced. And a low energy photon is something that will be, well, the electromagnetic spectrum goes from photons of very low energy to photons of very high energy. That's equivalent to saying that the light waves have very long wavelength, low frequency, to very short wavelength, high frequency. The different kinds of, so you go from very low energy, long wavelength, low frequency, that's radio waves. As you move up to sort of higher energy, shorter wavelength, etc., you get to infrared light. Then you get to this very narrow band of visible light. Then you go to ultraviolet. Then you go to X-rays, gamma rays. So depending on the temperature of something, it will tend to emit photons that have energies in a certain range. And it never emits photons with a very specific energy, something like a laser or something like a specific, well, let's not get into that. You can set things up so that you are emitting, like a sodium lamp emits photons of a very specific wavelength, or very specific energy. But when you're just heating things up and you're using sort of heat and just sort of random bouncings around of atoms to produce these photons, they will have a distribution of energies. And that distribution of energies will have a certain peak. There'll be an energy where there'll be an energy there'll be a most popular energy, and then there'll be some distribution of energies. Okay, so what happens is when you have a thing with low temperature, it's producing very low energy photons. And as you move up the temperature, the average energy of the photons that get produced gets progressively higher. Okay, so a key fact is around 6,500 degrees, well, 6,000, let's see, there'll be 6,800 degrees centigrade. No, I'm sorry, 6,200 degrees centigrade, around 6,000 degrees, 6,500 degrees. When you have a thing that is at that temperature, it's the peak energy of photons produced corresponds to the sort of the center of the visible light spectrum. And in fact, there's a distribution of energies of photons, and that distribution of energies goes from photons that correspond to red light to photons that correspond to blue light and everything in between, kind of a whole rainbow of light, of different colors. And those frequencies at 6,500 degrees roughly, something will produce, will be, if you were to look at the thing as you heat it up, it will look white hot. And it looks white hot because it is emitting photons with a distribution of energies, distribution of frequencies that corresponds pretty much to the range of colors that we see in invisible light. So just to explain that, the different colors correspond to different frequencies of light, different energies of photons. Low energy, the lower energy end is red light, the higher energy end is blue light. And that's, if you go outside the range where our eyes can actually detect the light, you go on the red end, you go towards infrared, on the blue end, you go towards ultraviolet. Okay, so light from the sun is concentrated in this range of energies of photons that corresponds to visible light. Okay, when the light has come in through the greenhouse roof and heats up your pots or the potted plants or whatever it is, those pots don't get heated up to 6,000 degrees, better not at least. And so those pots, because they're hot, are also emitting electromagnetic radiation, but it's not visible light. It's much lower frequency radiation. It's infrared radiation. And the issue is that, so light's coming in through the greenhouse roof. The greenhouse roof is transparent to visible light. But then what's happening is that visible light is being is heating up, the energy from that visible light is heating up the pots or whatever it is in the greenhouse. Those things are themselves emitting radiation, but it's infrared radiation of much lower frequency, much lower energy per photon. Okay, so what? Well, the point is that the greenhouse, which is transparent to visible light, is not transparent to infrared light. And so when the energy comes in through the greenhouse roof in visible light, it's then converted to energy that is associated with these lower frequency photons, these infrared photons, and the infrared photons then get stuck in the greenhouse because they can no longer, they can't escape because the greenhouse is not transparent to that infrared light. Now there are a couple of other effects that have to do with the well, there's also convection, and let's not get into that. But the basic effect is that the light in the form of that it comes from the sun, the frequency that comes from the sun can get into the greenhouse, but the heat, which is lower frequency, can't get out of the greenhouse. And so therefore, you just get more and more energy comes into the greenhouse, but it can't get out of the greenhouse. And so the greenhouse heats up. And the bad case for our planet, probably, is that the same thing happens there. And there are things in the atmosphere, like carbon dioxide, that can make the, that can have the effect that, again, light can come up, the light from the sun can heat up the surface of the earth, but the infrared light from the heat from the surface of the earth can't escape back into space again. And so on average, the temperature of the surface of the earth heats up. Now, there are many things that can affect that. For example, if you put aerosols into the upper atmosphere, or all kinds of things into the upper atmosphere that reflect the light before it ever gets to the surface, then you can change the amount of light that gets to the surface of the earth, and you can change the temperature. So, for example, what happened in the time of the dinosaurs, at the end of the time of the dinosaurs, when the 65 million years ago, when the asteroid hit the earth that wiped out the dinosaurs, or at least put the final last straw in wiping out the dinosaurs. One of the things one of the effects that had was it threw dust up into the upper atmosphere of the earth, and for a year or two, the upper atmosphere was just it was full of dust, and so light from the sun couldn't reach the surface of the earth, and so the earth dramatically cooled down. And if you're a cold-blooded dinosaur, that's bad news at that point. And so it isn't the case that at a different time in dinosaur history, there was, I think, a high carbon dioxide concentration, and the kind of joke thing to say would be, well, maybe that proves that the dinosaurs had developed an industrial civilization where they were burning coal from the Carboniferous period or something. We just don't know because all of that stuff was destroyed and we never found any evidence of it. But really, that was evidence of it. But that's nonsense. That's not what was going on, presumably. So I don't know. My guess would be that one of the things that limits carbon dioxide production in the Earth, for the Earth, and there are different sources of different kinds of gases, like volcanoes are a source of gases, and there are biological sources. One of the things that I would guess is that the more carbon dioxide you have, the happier the plants are, and so the more plants grow, and the more algae in the ocean, emerge to be able to process things and so on. And there's a whole sort of chemistry that can change. And certainly in I think the typical piece of carbon that is in there's sort of the cycle that happens on the Earth, where there's carbon in the rocks on the Earth, and there's carbon that gets the carbon dioxide, and I think it spends like hundreds of millions of years. The carbon spends sort of in the rock as one of the constituents of the rock. And only it's for some very brief period of history does it end up as carbon dioxide in the atmosphere. And then I think it's normally reabsorbed through the oceans. and then ends up back in the rock that forms, sedimentary rock that forms from the ocean and so on. And it ends up spending sort of most of its life in rock, so to speak, and only occasionally sort of emerges into the atmosphere. But my guess is that there's a lot of it in the atmosphere. There are more plants that happily grow. Now, of course, in modern times where we're sort of humans are in charge, so to speak, people will say, I don't want plants to grow all over this place where I'm trying to grow crops or something. I don't want giant trees there, or I don't want plants to go in the middle of my in some place where on my airport runway or something like this. So I mean, I think that what might be otherwise something where plants just grow wherever they can grow, and certainly many parts of the world had many more trees in the past than they do today. I mean, one of the things that humans have done is in the development of agriculture, when you're growing crops, you don't want a bunch of trees there. You want a plowable field rather than it covered with trees. And so, a lot of the US, for example, used to be covered with trees and then was turned into farmland, which is necessary if you're going to support, I think people estimate that sort of if you are just a hunter-gatherer, where you're not doing agriculture, you don't have crops that you have specifically specifically growing, the earth might be able to support 10 million people, very different from what you get when you actually have crops and agriculture and sort of an organized food production effort. So you kind of, that's what you get. And in order to do that, according to what the current agricultural practice, you can't have a bunch of trees there. You need light from the sun getting to your crops on a field, and you need to be able to, plow your field and so on. All right, long answer to that question. Let's see. Okay. Pavlidis is commenting about that limestone absorbs carbonic acid rain, so that's acid rain, scrubbing carbon dioxide out of the atmosphere, but it takes forever. I've certainly heard that there's a mineral called olivine, which is a green mineral that's pretty common, and I've certainly heard that if you put that like on beaches and you let it interact with the ocean and so on, that it is a much more efficient absorber of carbon dioxide. And I had heard that people who were, sort of saying they were going to make all the Earth's beaches green with olivine, and it was going to solve any problems with carbon dioxide in the atmosphere. That was a few years ago, and I haven't heard more about it. So something must have gone wrong with that scheme, I think. But people certainly, there's certainly some pieces of chemistry that can be thought about in those terms. Two Curbs asks, do the electron orbitals of an atom ever rotate? Do they rotate at the same rate as the nucleus or independently? Okay, is this the same property as electron spin or different? Okay, a lot of stuff to unpack there. All right, what is an electron orbital? So the general picture of an atom is there's a nucleus in the center. It's made of protons and neutrons, pretty small, and then the nucleus might have a certain size, and let's say 100,000. Let's say the size of the nucleus is 1 unit. Well, 100,000 units out is where the electrons that are part of the atom are sort of localized. So in an atom, the nucleus with protons in it is a positively charged nucleus, and it attracts electrons which are negatively charged. Electrical forces have the feature that unlike charges attract, like charges repel. Two protons will repel each other electrically, but a proton with positive charge and an electron with negative charge will attract each other electrically. Different for gravity, for example. For gravity, everything attracts, but for electricity, things which have this, like charges, both plus charges repel, but things with opposite charges attract. Okay, so in an atom, there will be the nucleus with positive charge, and it will be attracting the electrons. It'll be pulling electrons, saying, you know, get electrons, come and be part of this atom, so to speak. So, for example, in a hydrogen atom, the most common form of a hydrogen atom, just one proton in the center and one electron, one might say, sort of going around that proton. And when people first started thinking about this about 120 years ago, sort of the picture was more or less the electron would be attracted to the nucleus, much like a planet is attracted to the sun, and the electron would be sort of orbiting the nucleus like a planet orbits the sun. Now, that picture turns out to be very much too simplistic, but some of the terminology, like the term orbitals, comes from that picture. Okay, so why is that picture sort of too simplistic? The real reason is because of quantum mechanics. So let's see how to explain this. So quantum mechanics is this kind of very fundamental fact about things like electrons. And it says that whereas in ordinary physics, we think, oh, the planet moved in exactly this way. It's just one thing the planet did. Quantum mechanics says you shouldn't think about things that way. You should think about all the possible things the electron might have done. And that all those different histories, oh, the electron was in this place, it was in that place, it was moving that way, it was moving this way. All those different things that the electron might have done, they're all things that in some sense all really happen. And there's sort of many parallel threads of history and for the universe and for the electron, and every one of those threads of history is really happening. Now, the question is, why do we think that definite things happen? That's a very tricky issue that has confused people for a long time. And I think in our recent models of physics, we're beginning to have an understanding of that. And it's a little bit of a strange thing because in a sense, the reason we think definite things happen at some level is sort of tautologically because we think definite things happen. What do I mean by that? Well, there are all these different threads of history. This electron is doing all these different possible things, but our brain is also doing all these different possible things. So the question of what we perceive the electron to be doing is a question of what this sort of all the parallel threads, all this sort of branching threads of history of what our brain is doing, how all of those perceive all these branching threads of history of what the electron is doing. And so the important thing is that we think that definite things happen. So even though there might be parallel threads of history associated with our brain, we kind of conflate all those threads together. And the big fact about quantum mechanics is that we don't run into inconsistencies by doing that. In other words, if we just sort of assume they're all the same, then we don't end up with that doesn't lead us to sort of a global inconsistency. This is complicated stuff, and what I'm describing is kind of the sort of the leading edge of things that we figured out in the last few years in our project to understand fundamental physics. But the sort of the traditional, well, what comes out of this is the electron is doing all these possible things, and so you can describe kind of that there's a certain chance, a certain probability for the electron to do any particular thing. And there are equations that describe kind of what the density of probability is for the electron to do one thing or another. And so in particular, there's a thing called the Schrodinger equation, invented by Owen Schrodinger in the 1920s, which is an equation that tells you more or less the probability that an electron will, for example, be at a certain position relative to the nucleus of an atom. I'm eliding a couple of technical details here, but that's more or less what happens. And so that equation tells one, okay, this electron can, okay, so one feature of that equation is that it describes a possible probability distribution for the electron. But what it does is it describes a discrete set of possible probability distributions. So let me give you an analogy to this. So when you have something like a string and you pluck the string, one thing you can do is to pluck the string, and it kind of bows out, and there's just one bowing out from if you attach the two ends of the string. You can also pluck the string so that you end up with two sort of peaks in the string, or 3 or 4, but you can't end up with 3.5 because you've attached the string at one end, at both ends. Both ends have to be, in a particular place. But in the middle, the string makes a sine wave. It can make a sine wave with kind of a wavelength of 1, just bows out once, or 2, it does it twice, 3 does it 3 times, sort of 1 wiggle, 2 wiggles, 3 wiggles, but you can never get like 3.5 wiggles. It's the same thing with the Schrodinger equation with atoms, that you end up with something where this probability distribution for the electron can be kind of a 1 wiggle probability distribution, or 2 wiggles, or 3 wiggles, and so on. And those correspond to what people describe as the different orbitals for an atom. They correspond to different kind of states for the electron. Now, in each of those states, what's really going on is there's a certain probability distribution for exactly where the electron is found. So, for example, in the lowest state, the state with the lowest energy, the state, the distribution is such that in a hydrogen atom, for example, that the electron on average is a certain distance, the so-called Bohr radius, away from the proton at the center of the atom. And that distance is about 1/10 billionth of a meter. So that's but there's a distribution of distances. That's the average, but sometimes if you really were able to figure out exactly where was that electron, well, it was actually a little bit closer to the nucleus or a little bit further away from the nucleus, but that's the way it works. Now, one feature of that lowest level orbital, that lowest level state, is that it is spherically symmetric. That is, the probability to find the electron is the same in all orientations relative to the nucleus. Okay, as you go to the next state up, the first excited state, that's no longer true. What then happens is that oh boy, this is a little complicated. Okay, so yeah. So I mentioned with a string, you can have 1 wiggle, 2 wiggles, 3 wiggles, etc. When you end up with sort of a distribution of things on the sphere, it's a little bit more complicated than that. A string, it's just like one dimension, you're wiggling once, twice, etc. If you imagine putting things on the surface of a sphere, and you're coloring the surface of a sphere, and one way you can color it is just uniform color. Another thing you can do is say, you're going to have the equivalent of sort of 1 wiggle, but that corresponds to a certain coloring of the sphere. And it turns out that you end up with sort of 3 distinct kinds of colorings as the next level of coloring after just the uniform coloring. And so, technically those are they're called spherical harmonics. So the mathematics of this is in one dimension, the so-called orthogonal polynomials are sine and cosine functions. And on the surface of a sphere, the orthogonal polynomials are the spherical harmonics, which are related to things like things called Legendre functions. But in any case, the basic point is that what happens is that when you say, I've got an electron, and what state can it be in? Well, it can be in the lowest state, which is spherically symmetric. It can be in one of, it turns out, 3 possible next level states. And those 3 possible next level states have probability distributions that kind of, they kind of splurt out in different directions. So what do I mean by that? I mean, the chances are, for example, the electron is thinking about the spheres like the Earth. The electron is most of the time at the North Pole or the South Pole. That's one of the things that is sort of the next level of possible distribution of probabilities for where the electron is. Or there's another possibility, it could be on one side of the equator or the opposite side of the equator, or the same thing 90 degrees off. Those are different possible sort of independent configurations, that independent states that the electron can be in. And so those things are called orbitals for various reasons. The the lowest level state, the one that's spherically symmetric, is called the s orbital. These are named after German words that come from spectroscopy. They come from the light that's emitted when electrons transition from one of these states to another state. But in any case, the thing that so what then happens is the next level. So the s orbitals are the lowest ones. The next ones are p orbitals. Yes, it's in German, so I don't know exactly what the words were. But the next one is d orbitals, f orbitals, and so each successive, as you get to higher energies for the electron, it has a distant distribution of positions relative to the nucleus. And so when you see pictures in chemistry books, for example, of electron orbitals, they typically will there'll be the thing which kind of comes out in, let's say towards the North Pole and South Pole. It looks like two big jets coming out from the North Pole and South Pole. What that's doing is it's plotting, it's a little bit confusing perhaps, it's plotting as a function of direction, it's plotting the probability that an electron is found there as the distance from the center. So it's not really how the electron is arranged, it's just saying that's the probability that that's the probability distribution for the electron is such that it is more likely to be found at the North and South poles. So let's see, so then it gets even more complicated because, oh my. Let's see. The thing is, when you prepare an atom, you say, I'm making an atom. It comes out of a chemical reaction. It comes out of something else. The question is, are the electrons in that atom? Oh dear, this is complicated. We've talked about the fact that there are sort of three distinct states that electrons that have that are in these p orbitals can be associated with. Now, the thing that's tricky is those states are really just probability distributions. Each one is just the probability distribution for the one that is going straight up and down, the one that's left, right, the one that's in, out, whatever. Those are all just certain probability distributions. Now, in the end, an electron can be, and this is where sort of the story of quantum mechanics comes in, it can be in a so-called superposition of those states. And again, I'm kind of cheating a little bit because the superposition thing is adding up what are called quantum amplitudes, and the probabilities I've been talking about are the squares of quantum amplitudes. So there's a little bit of wiggling around here. But roughly, when an electron, when an atom is produced in some way, there will be some mixture. And let's say the electron has the energy that corresponds to the p orbital. There'll still be some mixture of the x and y and z orbitals that the electron, when you prepare an atom, there'll be some amount of, you're combining probabilities, there'll be some amount of the x orbital, some amount of the y, some amount of the z. And so when an atom is just, let's say an atom is produced in a chemical reaction, the electron will be in some superposition, some combination of x, y, and z, those x, y, and z states. And so when you say, what is the probability distribution? It'll be a mixture of those states. And so it'll be some probability distribution that's some fraction of one plus some fraction of the other and so on. Now, how does that probability distribution evolve? This is quite complicated. How does it evolve with time, for example? Oh boy, this is complicated. The issue is that this probability distribution is a stationary state. That is, if you have an atom and you leave it for a really long time, it will be in this s orbital state, the p orbital states, and so on. Those are states that things are in after a long time. So imagine the analogy with a string. Okay, so you've got the string, and eventually the string will just be in this state where it's, let's say, bowing, it has two wiggles in it, for example. But it could be that it got to that state by you know, using a bow and kind of, sort of pulling the string of one particular part of the string. The string was flapping around in all kinds of ways, and eventually it ended up being in exactly this this sort of so-called eigen mode. This thing where it always stays, eigen is German for same, where it always stays the same in some sense. But it can take a while to get, if you just say what happens immediately, it may not be in one of these staying the same states. So these orbitals, for example, are the conditions that atoms get into when it's an atom, which is, that's the way the atom is, and it's going to be that way forever, so to speak. When an atom first emerges from a chemical reaction or something like that, it's a slightly different description. And in that case, the this is going to get complicated, and I think we're going to run out of time here. But let me try to address this question had to do with the rotation of electron orbitals, and that is a really complicated story, because these orbitals are just sort of a picture version of some mathematics that's going on, and the thing I'm backing into explaining is that mathematics. But maybe I shouldn't go there. Let me just explain a couple of other things. So, yeah, this is complicated. Okay, so lots of things kind of spin around. So, for example, the nucleus of an atom can spin around its axis, just like the Earth spins around its axis. An electron can spin around its axis. In fact, every electron spins around its axis at a certain rate. Now, it's a little confusing because electrons are thought to have, although I don't think this is really true, but in sort of the traditional view in physics, has been electrons intrinsically have zero size, but they don't have zero angular momentum. So if you have a top, for example, spinning around, it has a certain angular momentum that's the velocity as it will keep spinning because of conservation of angular momentum. And an electron, it's zero size, but it has non-zero angular momentum. So it's a little confusing, but that's a feature of what is observed in physics. I think we now are beginning to know from our fundamental theory of physics why that might work that way. But in the past, it's just a fact that electrons have non-zero angular momentum, even though they have zero size. So the thing that that happens is that these different orbitals I've been talking about, they are also associated with angular momentum. And this is so confusing, because when we think about tops spinning around, we're used to the idea that you can look at a point on the top, oh, it spun around to a different place, it moved, okay? Unfortunately, the meaning of angular momentum in quantum mechanics is a little bit more abstract than that. And worse than that, when we're dealing with atoms and we're talking about these orbitals, these eigenstates, we're thinking about atoms that are kind of in a stationary state where there's sort of nothing, quotes, moving. And so this is a tricky story. Let me think about this, how to say this. Yeah, I mean, you see, the question of saying, oh, there's an individual electron and it's whizzing around the atom, that isn't really the right picture, because of this point about all these different possible histories occurring sort of at the same time. Yeah, I probably have to punt on this, because maybe I can come back to this another time. I'd have to explain a whole bunch of stuff about the way that quantum mechanics deals with angular momentum. And I mean, the end result is that when you think of a top spinning around, and you can kind of measure the speed that the top moves at, the outer part of the top moves at, that is a feature of classical physics. In quantum mechanics, you can't do something like that. You can't say, oh, I've got an electron, oh, it has an angular momentum. That means that I can look at a point on the electron and see it moving around. It doesn't work that way, not least because the electron is thought to be of zero size. The meaning of angular momentum is a little bit more abstract than just you can see a point on the thing and it's moving around. Now, it can be the case, yeah. And that's why one has to kind of understand more about what angular momentum means in quantum mechanics. And in the end, there is angular momentum. There are different kinds of angular momentum. There's I mean, just to say the technical terms, these orbitals are associated with what's called orbital angular momentum, which is kind of roughly the concept of the sort of an electron at a certain distance, and it's not really moving in the same sense. It's a mess. There's one of these cases where it's sort of a little frustrating, because if I were just talking about this in terms of the mathematics of quantum mechanics, although the mathematics is a little bit fancy, this is all pretty well defined. When it comes to interpreting it and explaining it in sort of everyday physics terms that we're all used to, where we're used to sort of our everyday experience of the world, it gets more difficult because quantum mechanics is not our everyday experience of the world. It's something different. All right. Well, I think I have to wrap up here because I have to go back to my day job. I look forward to continuing next week. And thank you for these questions. I think today we had a rather sort of physics-oriented collection of questions. I'm happy to, as I say, I always learn things by trying to explain them here. And thank you for these questions and some challenges here. All right, got to go now.